Hi, my name is Segarra, and I'm a third-year PhD student at Imperial College London. In this talk today, I will present our experience gathered over 5 years of using WebAssembly as an isolation mechanism for the cloud. After giving a very brief primer on WebAssembly, I will illustrate the benefits of using WASM as an isolation mechanism for 2 different projects. First, I will cover the usage of WebAssembly to isolate serverless functions in the context of the FASM serverless runtime. Second, I will cover the usage of WebAssembly to replace the thread and process abstractions for scientific applications using MPI and OpenMP. In the interest of time, I won't describe each project in detail. Instead, I will just describe what key benefits of WebAssembly each one utilizes and what benefits therefore unlocks. Lastly, I will outline what are the challenges we think WebAssembly still needs to overcome to become a de facto isolation mechanism for the cloud. So first of all, WebAssembly is a binary instruction format. WebAssembly can be used as an intermediate representation for a variety of programming languages in a CPU-agnostic manner. This is because WebAssembly can be defined as a compilation target in, for example, the LLVM toolchain, meaning that any programming language with an LLVM frontend can be compiled to WebAssembly, like C, C++, Go, Rust, or Swift. This makes WASM language independent. The design of the binary instruction format makes WebAssembly memory safe. WASM has a very simple memory layout model whereby all WASM state is self-contained in a mutable array of contiguous bytes. Pointers are represented as offsets from 0, and each memory access is bound checked. Offsets are expressed as 32-bit integers, which means that a WebAssembly module is limited to a 4 GB address space, but also means that bound checks can be better implemented using virtual memory and memory page protections. Other pointers, like function pointers, are expressed as indexes in tables, this allowing any kind of sandboxing scale. Most importantly, WebAssembly's memory safety has been formally verified. WASM's design and execution model is platform independent, meaning that the same WASM bytecode can be executed wherever a WASM runtime may be running, be it Intel, ARM, or RISC-V. A WebAssembly isolation unit is also called a WebAssembly module. And note that, again, the WASM runtime and all the different WebAssembly modules live in the same process address space. That being said, WASM isolated code cannot access the host environment, which means that it cannot access the network or the file system or the memory subsystem. WASM provides a standardized system interface, WASI, that defines the API through which WASM modules are to interact with their host environment. Things like memory management, i.e. mmap, may not always require interaction with the host operating system. However, things like file management through fopen, more likely than not, will always require further platform-specific implementation, with, for example, system calls in Linux. Now, I will describe the usage of WebAssembly as an isolation mechanism for serverless. Given its memory safety, isolation guarantees, and language independence, we thought it would be a great candidate. And this is the work we presented with FASM. FASM isolates serverless functions using fastlets, which are WebAssembly modules hardened with C groups and network namespaces. Fastlets can be easily spawned from snapshots of other fastlets by mapping the child's linear memory to the parents with copy and write semantics. Such a mechanism allows FASM to pre-initialize fastlets using proto-fastlets, whereby some initialization code is run on the fastlet, the linear memory is modified, and then another fastlets can be spawned from the modified linear memory, allowing to run some initialization code, for example. The results presented in the paper show that fastlets have considerably lower startup time than Docker containers, and many more fastlets can be packed in the same server, making a much more efficient use of the underlying resources. Additionally, we modified the WASI system interface code to accommodate for serverless needs, making it very easy for functions to communicate and share data between them. This makes distributed ML training in FASM considerably faster and more scalable than with Knative, a state-of-the-art serverless runtime. In summary, using WASM's memory safety, isolation guarantees, and language independence, we can replace VMs or containers for serverless function isolation, thus making a much more efficient use of the underlying resources, reducing cold starts and execution times. We then moved on, moving forward, we were thinking what other benefits of WebAssembly were there at reach to improve existing cloud applications. we realized that WASM's self-contained execution environment and limited interaction with host resources via WASI made it possible to design a very lightweight snapshotting mechanism. We enhanced fastlets with snapshotting capabilities and some other features and named them granules. Granules have the negligible execution overhead, memory safety, and resource efficiency of fastlets, but can also be snapshotted for preemption, live migration, or fault tolerance. Using granules instead of threads and processes, we can make long-running scientific applications using MPI and OpenMP migratable, elastic, and fault tolerant. This is important because OpenMP and MPI applications, once deployed, cannot be migrated to improve locality, elastically use either resources, or recover from partial failures. In the interest of time, I will cover the details of the technical contributions for which I recommend checking the pre-publication or archive or shooting me an email. Note that this work is still in progress, so we're planning on submitting it later this year. What I will do, though, is I will show a demo of a simple MPI application that, by using granules instead of threads and processes, can be live migrated mid-execution without any changes to the application source code. In this video, I will spawn an MPI application that does just all-to-all communications in a tight loop. Originally, as you will see, the MPI application is spawned over two different workers, as you see through the logs on the very bottom bit that I will highlight. In the middle of the execution, we will migrate two of the ranks that are running in a remote host to the local host. You will see that this very much improves the execution time. The observation is therefore that by making MPI applications migratable, we can benefit from changes in the resource availability in a shared cluster, thus reducing execution time. As you see now, the iteration of the loops are running rather slowly, and eventually, migration will happen. You will also notice that there's a radical difference in execution time between the original iterations and the iterations once all runs are collocated. Again, this is with no changes to the application code. Even though WASM has proven to be a competitive alternative to containers and VMs for serverless functions and threads and processes for OpenMP and MPI, there are still a number of issues that, in our opinion, block its widespread adoption. First of all, WebAssembly has no storage outside of the CPU. In the era of large-scale heterogeneous and disaggregated computing, WASM could be used as a universal execution format to implement a code shipping architecture. However, the existing lack of support to run on heterogeneous devices like GPU or FPGAs challenge this vision. I personally don't think WebAssembly will ever run inside a GPU. Instead, the focus should be making on WASM transparently executable in any kind of wimpy CPU and define well-established system interfaces to access hardware accelerators like GPU through WASI. Second, and in my opinion most importantly, WASM does not have support for hardware-based WASM module isolation. As previously described, WASM modules run in the same process address space, and their safety relies not only on the memory safety of the instruction format, which is formally verified, but also on that of the WASM runtime implementation. Unfortunately, this is not enough security for a true multi-tenant cloud environment, as hypervisor-like hardware isolation is mandatory to isolate functions belonging to different users. There has been an upheaval of research in lightweight hardware isolation mechanisms through hardware memory capabilities or unikernels. These technologies usually compile applications by linking them to kind of like a libOS to run general purpose applications. But maybe WebAssembly and WASI compliant apps could drastically change the landscape of supported applications by opening up the doors of these special purpose hardware isolation mechanisms to generally available applications compiled to WebAssembly. Lastly, WebAssembly has a very active community and a very active set of skillful software engineers from big tech corporations. Things like in WebAssembly threading, support for dynamic language runtimes, or 64-bit WebAssembly are just around the corner and a matter of time. That being said, there's still a lot of space to do research on the application of WebAssembly as a new isolation mechanism for the cloud. Thank you very much for your attention, and I'd very much like to take questions over email or through any other means. Thank you very much.